Hello, and thank you for watching the video. My name is Arne Meier, I'm from Hanover, and this video is about our STACS paper, Parameterized Counting in Logspace. This is joint work with Anselm from Hanover, and Raghu from Chennai. Let me start by outlining the scope of our work. Here you see three areas of research: parameterized complexity, space complexity, and counting complexity. We want to focus for this talk on parameterized complexity, and we want to look at the intersections with the other two areas. First, in the intersection with counting complexity, you can see two works who have founded this area of research. The first one is Flum and Groer, the parameterized complexity of counting problems in 2004, and McCartin in 2002, parameterized counting problems. For the intersection of parameterized complexity theory with space complexity theory, you can see the foundations laid out by Elberfeld, Stockhusen, and Tantau. In 2013, completeness results for parameterized space classes, and in 2015 on the space and circuit complexity of parameterized problems, classes, and completeness. For the last intersection, so the intersection of all three areas, this intersection has been empty until today. We start here with the foundations of parameterized counting in Logspace and give you a framework where you can do research in the intersection of all three areas. Let us proceed with the motivation and overview of this research. We want to improve the view on para-Logspace-based classes. By this, we want to build on the parameterized space classes by Elberfeld et al. From the papers I mentioned on the slide before. We want to understand the landscape of counting problems on that particular level, and we approach this by studying different manners of accessing non-deterministic bits, when they are accessed and how they are accessed. As a brief overview of our results, I want to give you these 3 points. First, we created a theory of para-Logspace counting. Then we will show several natural problems that are complete for our classes. And finally, we formulated a list of connected research questions. Before we start with the formal definitions, I want to say a few words on the considered machine model. We use an intermediate model between Turing machines and word RAMs. That is, Turing machines with random access to the input tape. So we have, for this purpose, we have a random access tape. And our Turing machines can query relations in input structures in constant time. For this, we have a relation query tape. We view a non-deterministic machine as a deterministic one with an additional two-way access choice tape, which is read-only. Why do we use this? It seems that random access seems to be necessary in our setting. I will talk a little bit on this a little bit later. And still, this model has the same computational power as Turing machines and RAMs, but guarantees certain robustness in our setting. Also, in parameterized complexity theory, it is not uncommon to use this random access machine model. Now a few words on parameterized complexity. In parameterized complexity, we study parameterized problems. For every problem, we identify a parameter, and because of this, we represent instances as tuples of binary strings together with a natural number, the parametric value. The motivation for that is that the complexity of a problem usually not only relies on the size of the input. There is something else where we can pin down a more fine-grained analysis, allows to pin down the real source of intractability of a problem, for instance. Also, we want to tame the combinatorial explosion of the problem space and want to pin it to the parameter value. Problems that are solvable in time f of k times poly of the input length are called fixed parameter tractable problems, or short in FPT. Here, this is some computable function f, and this runtime has to hold for all inputs xk. Now we proceed with talking about when the bits and how many of the non-deterministic bits are accessed. Let us look at two definitions first. For k-bounded Turing machines, at most f of k times log of input length many non-deterministic bits are read. If the machine is tail non-deterministic, then after the first non-deterministic bit has been read, at most f of k times log of x many further steps are allowed to be done. Here also f is a computable function, x is the input, and k is the value of the parameter. In 2003, Chen, Flum, and Groer were able to show that WP, this complexity class in the parameterized world, coincides with all parameterized problems accepted by k-bounded FPT machines with a choice tape. W1 has been characterized as all problems accepted by k-bounded tail non-deterministic FPT machines with a choice tape. So here you can see that between WP and W1 there is a difference between tail non-determinism and no tail non-determinism. In our setting we will see that for a particular class this tail non-deterministic behavior seems to be irrelevant. Now I want to say a few more words on accessing these non-deterministic bits. I mentioned before that we want to distinguish between how, so read once versus unrestricted access, versus and also when, tail non-determinism versus unrestricted. How do these variants differ in the setting of parameterized log space counting? So FPT with k-bounded non-determinism is WP, while FPT with k-bounded tail non-determinism is W1. Read once access on this level never matters. We can always store the non-deterministic bits that has been accessed during the computation. Now we want to proceed with our formal definitions of the complexity classes we introduced. And that is about parameterized counting in log space. So we consider parameterized functions, here short PF, that are functions similarly as for the parameterized problems are tuples. The inputs are tuples, so we have a binary string and a natural number, the parametric value, and it maps to a function value. So now it maps to some natural number. Parallel log space is then also the space restriction to the space O of log of input length plus f of k. And now we can find the first definition. So sharp para WL is the class of all parameterized functions that are computed by k-bounded parallel machines M. That means for all inputs xk, the number of accepting paths of the machine coincides with the function value of this parameterized function. If we impose further restrictions on this k-bounded parallel machine M, then we get the other classes that we defined. So we make here restrictions depending on if this machine additionally is tail non-deterministic, so at the end of the computation, in a sense in the tail only the non-deterministic access happens, and the other restriction is having read once access to the non-deterministic bands or allowing multiple passes on the choice tape. So the first class, sharp para beta L, that we consider has only read once access, while W1L has the property tail non-deterministic, and para beta tail has both properties. Further note that the class beta is between W and beta tail, and the W1 class is between W and beta tail situated. This follows immediately after these definitions. So we consider here three types of paralog space reducibilities, namely Turing, metric, and parsimonious reductions. So Turing is the most general one here. Any oracle parameter is bounded by a function in the input parameter. Then we get further restrictions down to parsimonious. So for metric reductions, only one oracle query is used. And for parsimonious reduction, additionally, the answer of the first query has to be returned. We can show that the classes #para_WL and #para_BetaL are closed under parsimonious reductions, and all four classes are closed under addition and multiplication. We want to close this slide with the question whether some of these classes are closed under the prominent monos operation. That means the maximum of f minus g and 0. Other closure properties might be worth studying as well. Now we will start with natural problems complete for our classes, beginning with counting walks. The first problem, P#reach, is defined as follows. The input is a directed graph GVE, two vertices ST and a natural number K. Here and in the following slides, K is always the parameter of our problem, so we do not explicitly mention it here in this problem environment. The task is to compute the number of ST walks of length exactly K. So we count the number of ST walks of length exactly K to be precise. We are able to show that this problem is complete for both classes, #para_BetaL and #para_BetaTailL with respect to parsimonious reduction. So on this level, the tail nondeterminism has no difference. Yeah? So these classes are more or less the same under the parsimonious reduction closure. So this is a set of all problems that are parsimoniously paralog space reducible to some problem in that class. So that means what you see here in this corollary summarized, and these two classes with respect to these reductions coincide. Now we want to proceed with the second kind of problems that are complete for our classes. And this is a setting of predicate logic, so we want to count first order assignments. Here as a notation in the beginning, phi of struct A is a set of satisfying assignments of phi in the structure A. So the problem is now about model checking, and that is why it is called P# MC F. A is a natural number and F is some formula class. As input is given a formula from this particular class, a structure A, where the arity of each relation is bounded by A. So this is fixed for the problem, not part of the input, the A. And the parameter again is a natural number K. What do we want to count? We want to count the number of satisfying assignments of phi in A if K is equal to the formula length and 0 otherwise. We want to make a further restriction for formulas, which is called R-local formulas. And the formula is R-local if the distance of two atoms sharing the variables is less than equal to R in the depth-first search run on the syntax tree of phi. So this is a pure syntactical restriction. And we want to introduce the notation sigma 0 R-local is a set of all R-local sigma 0 formulas. So the sigma 0 formulas are formulas without quantifier alternation. And then we are able to show that for all A, for all fixed arities greater or equal than 2, for all localities R greater or equal 1, this problem is #para_BetaL complete and #para_BetaTailL complete with respect to parsimonious reduction. So here again, this tail nondeterminism has no real effect, it seems. So if we drop both restrictions of the previous slide, then we get a #para_W1L complete problem with respect to parsimonious reduction. So in a sense, this poses the question, if we only drop one of these restrictions, so either locality or either arity, then what is the complexity of the parsimonious paralog space closure of this problem? And also the question is, if we consider the parsimonious paralog space closure of the class #para_W1L, what kind of maybe known class could this be? The third kind of problems we studied are homomorphism problems. So we want to count homomorphisms. So the input is given a pair of structures A, B, where A is from the fixed structure class calligraphic A, and K, our parameter again, is a natural number. And we want to count the number of homomorphisms from struct A to struct B if the domain size of struct A is bounded by K and 0 otherwise. Here we can show that this problem is para-beta L complete with respect to parsimonious reductions. And this is possible for only this structure class P star, which are colored paths. So the question is there any natural class of structures such that we get completeness for W1L? The last problem that we considered in our setting was computing the determinant. Here S and K is a set of all permutations of the numbers 1 to n that modify exactly k items. So n minus k items do not change. And the problem P det is defined as follows. We are given an n square and an n times n square matrix A and a parameter k in n. And we want to compute this following sum here, which is essentially the determinant restricted to these S and K permutations. For this particular problem, and we are able to show for 0, 1 matrices that they can be written as a difference of two functions in sharp para beta tail L, and this problem is sharp para beta tail L hard with respect to metric reductions. So here the question, of course, is what is the precise complexity of this determinant? Maybe you have an idea. Now we want to almost finish by showing you an overview of our results. Here you see the complexity classes that has been introduced by us and also complete problems that we have shown to be a part in this particular classes. This arrow means a problem is complete for the particular class where the dot is with respect to the reduction that is mentioned nearly at the arrow of the dotted line. And then we have also here some further problems. For instance, P sharp CC to CNF. CC stands for cycle cover. And on these edges there are some CNF formulas mapped. Then we have log reach and log walk. You can see the details in our paper. So for instance, the uppermost problem is complete for sharp para WL under parsimonious reductions. Then there are also two dashed areas in this graph, and the question in a sense, what kind of areas could be empty or not, and this was with respect to this bounded arity but no locality, and locality but not bounded arity, where we had these two questions presented to you a few slides ago. Now I want to close this presentation. So as results, we introduced a new theory of parameterized log-space counting. We presented a list of several natural problems complete for the classes. So the first one was these reachability questions in graphs. Then we studied the counting FO assignments, and then we talked about homomorphism countings, and lastly we considered the parameterized determinant. We also presented quite a long list of future work and cordially invite you to think about these questions. So we want to study further closure properties, so monos and others are worth studying. We want to improve our understanding of the influence of syntactic locality, respectively bounded arity, in the setting of counting FO assignments. We want to characterize the parameterized log space parsimonious closure of sharp para W1L. For the homomorphism problem, we had this result regarding these colored paths, but now we look for a structure class that could be able to characterize sharp para WL. Also, we want to address satisfiability questions to get a new kind of problems in this level and to see what kind of structure these problems have that can yield completeness results for our classes. And then we want to study the descriptive complexity of our classes and highlight the robustness of our classes. Finally, the studying gap classes might improve the result on the determinant. Thank you very much for watching the video, and feel free to join our live presentation given by Raghu. You can see the full version of the paper with all proofs on arXiv 1904.12156. And we also thank for the Indo-German cooperation grant given by DAAD and DST, which made it possible to travel between Hanover and Chennai. Lastly, whenever you have questions, feel free to contact me or Anselm, Om or Raghu. Then I wish you a nice day. Thanks.